So hello everyone for this early session previews. We start with a bio talk from Arjun Guha, who will be previewing the session on format methods in compilation and implementation.
All right, thank you everyone for coming bright and early. So I'm going to preview the session on formal methods in compilation and implementation. So there's three really cool papers in the session. The first one is tail recursion modulo context and equational approach by Dan and Anton. So just to recap, tail recursion and tail calls are of course fundamental to functional and object-oriented programming. Without tail recursion, you kind of have to use loops and imperative features to get the performance that you might want from programs. It's not just about performance, it's also about sort of fundamental time and space complexity guarantees, right? So for example, this version of length is not tail recursive. You can sort of rewrite it using a loop if you want to use imperative features, but in a functional language that supports proper tail calls, you can rewrite this function using an accumulator and get a version of length that does not sort of consume linear stack space. Okay, so now not all functions, of course, can be rewritten to sort of exploit tail recursion. So think of like the function map, for instance. If you want to write a version of map that traverses the list exactly once and also doesn't consume sort of linear space beyond the new list that it's going to construct, you can't really pull that off with immutable lists, right? What you need to do, well, if you're in a programming language working with data structures that support things like extensible arrays, like in Java, JavaScript, for instance, you can pull this off, but using immutable lists, which are typical in functional languages, map seems to need to use extra stack space. So it may seem like there's no good solution in a functional programming language with immutable data structures, but there's this well-known technique called tail recursion modulo cons that allows you to sort of pull off an in-place update under the hood. And there's been some recent work by the authors of this paper that sort of exploits this to get sort of precise garbage collection, reference counting and garbage collection. This was in, I think, PLDI a year or two ago. So what this paper does is it generalizes tail recursion modulo cons to tail recursion modulo context. So it shows for the first time how to use equational reasoning to argue that these transformations that use lots of low-level tricks like in-place updates under the hood, why these transformations are correct. So a problem with tail recursion modulo cons, tail recursion modulo context, is that it doesn't quite work in the presence of sort of advanced non-local control flow features like algebraic effect handlers and continuations. But another thing that this paper does is it shows you how to get tail recursion modulo context and algebraic effect handlers to work. So this is done in the context of the Coca language, which supports algebraic effect handlers. So I would say, sort of to summarize, like if you're building a functional programming language and you want functional programming to really shine, so not just work, but sort of perform as well as the sort of imperative counterparts, this is a really cool paper to read. It sort of shows you how to make functional programming really work and really perform well. So the next paper in this session is executing microservice applications on serverless correctly, by Konstantinos Kallas, Haoran Zhang, and their advisors. So large web applications these days rely on replication for scalability. It's like the only way to support applications with millions and billions of users at scale is to have hundreds and thousands of machines. Demand is also spiky for web applications. Some hit video happens and demand sort of easily goes up by a factor of 10 or whatever. And also, that demand is, of course, unpredictable. And also, these large web applications are often structured using a sort of cluster of like microservices. So for example, when you visit, say, I don't know, let's say the Twitter homepage, there's like one microservice serving you the news feed and another microservice serving you, whatever's trending, and another microservice serving the other, like more boring parts of the GUI, who knows. For some of these applications, viewing a single page may involve firing up, hundreds of microservices on a whole bunch of machines. So serverless computing, well, firstly, it's a poor name. Like, of course, there's servers. The idea behind serverless computing is that it's an abstraction that allows programmers to not have to think about how many servers that they're working with. There's, of course, servers under the hood, but it's a cloud computing abstraction where the cloud platform takes care of starting and stopping, allocating and deallocating servers for you. It takes care of sort of things like fault tolerance under the hood. It's a nice abstraction in a way, but it comes with a whole bunch of problems. In particular, requests can get reordered. You have to sort of worry about sort of concurrent, a lot of concurrency and so on. So there's been a couple of recent papers at like UPLA and PLDI. This is, I think, the third paper in a sequence of papers by a bunch of people in the community that sort of takes a PL lens to serverless computing. The earlier work made a bunch of simplifying assumptions, and I can say that because I did one of them. But this paper really gives you a sort of comprehensive treatment of serverless programming with microservices. There's this sort of very simple high-level language that's sort of built in Python that sort of compiles down to a lot of like gnarly code under the hood. So if you want to learn about serverless computing and see a really nice solution to it, this is a cool paper to look at. And so the final paper in the set is taking back control in an intermediate representation for GPU computing. So I couldn't find an XKCD, but this is an XKCD that apparently makes GPUs crash, at least it did at one point. So this is a really great example of PL research making rapid impact on languages that everyone uses. So this paper is about SPIR-V, which is an intermediate language for, you can think of it as analogous to LLVM, but for GPU programming. SPIR-V is the IR to which a lot of higher level languages compile, and SPIR-V is then compiled down to various GPUs by various vendors. The paper is a sort of it's a really cool paper where the authors went about formalizing SPIR-V using the Alloy analyzer. And if you are not familiar with the Alloy analyzer, I recommend attending the talk. It has a bunch of really cool insights on how to use it effectively. It's a form of like lightweight formal methods that's very different from, say, verification in Coq, which more people may be familiar with. The thing that they focus on is formalizing how control flow works. Okay, this is very distracting. How control flow works in SPIR-V, and it sort of reflects a lot of like the weird things that happen with control flow in under the hood in GPUs. The paper comes up with a formal spec of SPIR-V control flow and Alloy, and from that formal spec comes up with examples that sort of exercise corner cases of the SPIR-V spec. There's this really cool approach to fuzzing that I don't want to get into in detail. You know, tend to talk for that they use to sort of fuzz SPIR-V implementations. They find bugs in all sorts of compilers by all sorts of people. These are all compilers that we are using in our computers. At the end of the day, they managed to come up with an update to the SPIR-V specification that has been accepted and is in the next version of SPIR-V. So you may be wondering how these three talks are connected together, and I'll let you think about that while Jan comes up and talks about the next session.